Hello friends, today we will see Michelson's interferometer. See, an interferometer is an instrument in which the phenomenon of interference is used to make precise measurements of wavelengths or distances. For particularly a Michelson's interferometer, it deals with the principle that is a beam of light from an extended source is divided into two parts of equal intensities by partial reflection and refraction. These beams travel in two mutually perpendicular directions and come together after reflection from plane mirrors. The beams overlap on each other and produce interference fringes. See, this Michelson's interferometer. Now we will see the construction of this Michelson interferometer. In this diagram, we are able to see the G1 which acts as a beam splitter, then G2 which acts as a compensating plate, and there are two mirrors M1 and M2. The beam splitter G1 is partially silvered plain parallel glass plate. The compensating plate G2 is a simple plain parallel glass plate having the same thickness G1. See, the two glass plates G1 and G2 are held parallel to each other and they are inclined at an angle of 45 degrees with respect to mirror M2. The mirror M1 is mounted on a carriage and this M1 can be moved exactly parallel to itself with the help of micrometer screws. The distance through which the mirror M1 is moved can be read with the help of a graduated drum which is attached to the screw. The displacements of the order of 0.1 micrometer can be easily read. Then the plane mirrors M1 and M2 can be made perfectly perpendicular with the help of the fine screws attached to them. The interference bands are observed in the field of view of the telescope T. This is about the construction of this Michelson's interferometer. We will see how it works. See, in the diagram, monochromatic light or source S is rendered parallel by means of a collimating lens L and is made incident on the beam splitter G1. Then this ray is partly reflected at the back surface of G1 along AC and partly transmitted along AB. The beam AC travels normally towards the plane mirror M1 and is reflected back along the same path and comes out along AT. The transmitted beam travels towards the mirror M2 and is reflected along the same path. It is reflected at the back surface of G1 and proceeds along AT. The two beams received along AT are produced from a single source through division of amplitude and are hence coherent. The superposition of these beams leads to interference and produces interference fringes. From this figure, it is clearly seen that a light ray starting from the source S and undergoing reflection at the mirror M1 passes through the glass plate G1 three times. On the other hand, in the absence of plate G2, the ray reflected at M2 travels through the glass plate G1 only once. For compensating this path difference, a compensating plate G2 of the same thickness is inserted into the path AB and is held exactly parallel to G1, and hence here we are getting the Michelson's interferometer, and by which we get the interference pattern. Thank you very much.
मित्रांनो, आपण मायकेल्सन्स इंटरफेरोमीटर ह्या एक्सपेरिमेंटची experimental arrangement we have already seen, and see, for observing the interference pattern and by observing it we can determine the wavelength of light used, and we can detect the difference between two wavelengths also. These are the applications from Michelson's interferometer. Now we will see using the Michelson's interferometer how are the fringes, or we can say what are the types of fringes which we get by using the interferometer. See, there are three types we can say. One is a circular, another second one is localized fringes, and third one is white light fringes. Friends, here we will see one by one. First of all we will see about circular fringes. By its name circular, it indicates the fringes are circular one. What or how the circular fringes are produced? See, when we are discussing the types of fringes at that time, you should remember the experimental arrangement of Michelson's interferometer. Means that there are two mirrors, they are exactly we have to keep perpendicular to each other, and there is a compensating plate. All these things you have to keep in mind. Then you can be able to understand or the concept of these fringes. See here, the circular fringes are produced with monochromatic light, and when and only when the mirrors M1 and M2 are exactly perpendicular to each other. See here, when they are exactly perpendicular to each other, and the origin, what should be the origin? It can be understood by following things. If we look into the instrument from T, for this again you have to remember the experimental arrangement for the Michelson's interferometer, which we have already seen. See, in that there is a mirror M1 directly, and in addition to it, we can see the virtual mirror M2 dash of the mirror M2. This M2 dash is the virtual mirror image of mirror M2, and which is formed by the reflection of the glass plate G1, and this can be seen here in the diagram also. In the diagram you can see this M2 dash. This M2 dash is nothing but the virtual image of mirror M2. It means that one of the interfering beam come from M1, this M1, and the other beam appears to come from the virtual image M2 dash. This one virtual image is coming from M1, another one is coming from M2 dash, and the situation is similar to an air film enclosed between mirrors M1 and M2 dash. There is the formation of air film takes place, and with the difference in the case of a real film between two surfaces, multiple reflections takes place, whereas in this case only two reflections takes place, and therefore the total path difference between these two beams, the beam coming from M1 and beam coming from the virtual mirror M2 dash, this is the optical path difference equals to 2d cos of theta plus lambda by 2. And see friends, the condition for obtaining the brightness or bright fringes, 2d cos of theta plus lambda by 2 equal to m lambda, where m is nothing but the number of fringes, that is 0, 1, 2, 3, and by which we are getting the circular fringes. Yes. Now what about the localized fringes? See now, what is the condition for localized fringes? See here again, when two mirrors are tilted, these two mirrors, if they are tilted, means they are not exactly perpendicular to each other, and therefore the mirrors M1 and the virtual image M2 are not parallel. For this, again, remember the basic diagram of the Michelson's interferometer, in which M1 and M2 are perfectly perpendicular to each other, but when they are tilted, means that they are not perpendicular, exactly perpendicular to each other, therefore the mirrors M1 and the virtual image M2 dash are not parallel. Then what happens in this case? The air path between these between them is wedge shaped, and due to that wedge shaped, already we have discussed the wedge shaped things, and the fringes appear to be the straight. If one of the mirror is moved, the fringes move across the field. Then the position of any particular bright fringe is taken up by the one next to it. Then the fringes can be counted as they pass a reference mark. If m fringes move across the field of view, then m1 moves through a distance d. Then see here, d equals to m lambda by 2, or here lambda is can be calculated by 2d by m. This is the formula for calculating the lambda. In this way we can have a calculation for determination of lambda, value of lambda, by the use of localized fringes. Now third and last type of fringes is white light fringes. Means when we are using a white light such as a mercury, then a white light source is used for it, and few colored fringes with a central dark fringe can be observed. In observing these fringes, the mirrors are slightly tilted. As we have been done the process for the localized fringes, and the position on M1 is found where it intersects M2 dash. This position is often difficult to find with white light. Then the position can best be located with a monochromatic light when the fringes become straight. Then a very slow motion M1 in this region using a white light will bring these fringes into view. When a central dark fringe is surrounded by 8 to 10 colored fringes on either side are observed. These fringes are useful for the determination of zero path difference. And friends, if we having the means here we have in a photograph for the white light fringes. In this way we can observe the white light through our telescope tube and we get the pattern in this way. Friends, in our total we have been seeing the Michelson's interferometer and as well as the types of fringes for the interference pattern. The next article we will see in next lecture. Thank you very much.